Welcome everyone to episode 7 of calculator programming. Today we're going to... It was really hard for me to decide what we're actually going to do today. But I'm thinking... well, actually I'm kind of still deciding. I was thinking there's kind of three choices. One of them was I might try to make like something fun, just really short and simple, like a random sentence generator. Something that I don't think would really, it contains some debugging, but the debugging would never be some like really complicated. Then I also thought maybe we could work on Zelda. But actually, now that I opened up my programs window, I'm wondering if I should show you these other programs that I've made in the past. I've had programs on a calculator that have all gotten deleted plenty of times before, so these ones actually are pretty recent. Like, I've made these within just usually they're only like up to like a year old, and then something happens and I lose my memory on my calculator, but I never really lose anything too important anyway, so it's not a big deal. But here, Snake is a game that I made. You move around, you collect the dots, and it's actually really simple the way I programmed this. I just have a matrix for the background, and then I have a list for the snake. And I don't remember if I really had to do too much debugging on this. I might have, but the programming of it is, you can just imagine Fall Down, but just a different game. It's similar to this, although the Fall Down was really, really, really bad because it took me forever to debug, and I was brain dead for the longest time. For some reason, I just couldn't think. But yeah, there we go. My length is 57. Let's see here. What else did I make? Fast. Oh, this, you can just keep increasing your speed, and that dot shows like the background. So basically it's just a wrap the screen type thing where I can move, like I can move down if I want. Yeah, it's not too exciting. It's just a little game where you just move. And I wanted to put like, here, Towers of Hanoi. This is a nice one. I made this one time. I just couldn't sleep. It was in the middle of the night. It was like 1 in the morning or something like that. And I couldn't sleep. I wanted to feel better about the day. I think I finished some kind of programming project, but I didn't feel like creative for it. I just felt like I had to get it done for the deadline. And then in the middle of the night, I was just like, okay, I want to do something, 10 times easier than what I just did. So I'll just program my little calculator here, but it was still kind of a challenge just for myself, but it wasn't something that would be like impossibly hard to debug. So I made it. It's not a Hanoi tower solver. I mean, I know how to make that, but I just wanted to make something where you actually can do the Hanoi towers yourself. So anyway, the way this works is you use left and right, and the second key picks up and drops numbers. So I can move this 1 wherever I want. I can put it right there. I can move the 2 here, put the 1 on top of the 2. Okay, and the way you solve this, some people like have a lot of trouble solving it, but it's actually a really simple algorithm. Like, it's a recursive algorithm. When you program a computer to do it, you say, okay, to move this entire tower here, first I want to move the smaller tower here, and then move the bottom piece here, and then move the smaller tower back. But in order to move the smaller tower here, you have to do the same thing with even the smaller tower to move it here, and then the bottom piece here, and then move that rest of the tower back. But in order to move that tower, it's like the same thing. So it's like the problem breaks down. But it's kind of hard to think that deeply. But if you notice, it's just switching every time. So like if it's odd, it'll be in the other position than when it's even. So like for example, I'm going to move the 4 here, and then to move the 3 stack here, I have to move the 1 here first, because the 1 is the same, it's odd just like the 3. So I'll move the 3 back onto the 4, and then I'll move that stack back up on top, and then of course I'm going to move the 5 here, and then eventually I'll move the 6 here, and then the 7 here. So it'll be really it's actually pretty simple to solve once you get the hang of it. You can just kind of do it without really thinking about it at all. Doesn't really involve much thinking once you get it down. So this was kind of fun to program. I just wanted to make something where you could control it, something where it functioned properly, but it looked cool enough to where you could see that you were actually grabbing it. There wasn't anything like invisible, or I wanted it straightforward so I could just show it to, you know, any random person and be like, here, you want to play, you know, Hanoi Towers? I made it on my calculator. So it's just a nice thing. You can just like challenge someone and be like, here, can you solve it with 4? Can you solve it with 5? Can you solve it with 6? But anyway, I'm not even like halfway done solving this yet, so maybe I should just stop. I guess I could show you me solving it. But anyway, the reason why I know I'm halfway done is because I haven't moved the 7 yet. And that's like literally like the middle move, like to move this 7 right here. And that's, I'm officially halfway done. And now to move everything back over here, I need to move the odd ones, like since 6 is even, we got to move the 1 over here. That's how I know the 1 goes on this side without having to like think, you know, too deeply about it. I just know it's the opposite. So yeah, eventually I'll get to the point where I can move the 6 back onto the 7, but it seriously takes a while. Oops. See, I made a mistake there. The 1 should go on top of the 4. Yeah, so, oh, and it counts my moves too. So because I made that mistake, yeah, that's another thing I added in this, because I wanted it to count your moves. So because I made that mistake, I'm not going to get the optimum number of moves, which is fine. It'll show you the difference, because it's 2 to the n minus 1, I think. 2 to the n and then minus 1, where n is how tall the tower is. That's how many moves it'll take. So I guess I could just solve this really quick. I'm almost done anyway. I know I'm at least 3/4 way there because I already moved the 6. So let's move the 3 stack onto the 4. Oops. And then move the 5 onto the 6. Move the 3 stack to the left. Move the 4 onto the 5. Right about now. And then we did it. So it's going to tell us how, like, our score, which is 130 out of 127. So the minimum number of moves would have been 3 moves less than what I did. So, and then it asks you to, if you want to play again. So if you want to just play with like 3, you know, that's easy. This, I think, is an in-between screen. I might show you what that is. Oops. Oh. I could have done it in much less. Oh, one less move. Anyway, is it list? What is list? No, that doesn't work. It's called challenge. That's the one. What this does is it uses my other games, but it sets a special variable that I check for in the other programs. So it says eat 10 dots, and it actually changes a variable that the snake program looks for, and it sets it so that I have to eat 10 dots, and once I eat 10 dots, and I think my length has to be like 14 or something once I eat 10 dots. But anyway, once I do that, then it has like a return variable that it uses. Or oh, it's supposed to pause there, but anyway, it says solve the Hanoi tower in 5 with 5 5 on the stack. But anyway, I never really finished that. I think it also tried to access another program down here, which I haven't shown you yet, which is math. This just asks you math questions, so it's actually pretty simple to program. I programmed this probably 2 or 3 times in my past. I've made it so it gets harder. So 2 squared is 4. 9 to the 6. What? That's really hard. I don't know. I'll just guess something. 423. Wrong. It's 4. What? Okay, maybe that's not correct, but what's 64 times 8? 48 plus, or wait, 4 times 8, 32 plus 60 times 8, 48 plus 32, so 512 or something? I don't know. Let's just guess. It's 4, what? Okay. I definitely need to fix something in here, because I definitely I think I stored the wrong number into the correct variable spot. I think I just did the wrong. Anyway, it looks like the powers isn't working. It's no big deal. If I want, if we want to work on it sometime, we could fix it or maybe program it from scratch or something. I think I made a quadratic program. RSA, I tried to make an encryption program that basically gives you creates a public-private key pair, so that you can, if you like suspect that somebody's like controls like your operating system, like Microsoft, spies on your keystrokes or something, you want to like send a super secret message to someone, but you don't already have like a private, cipher key with them. This would basically like help you generate it theoretically, but yeah, it took me, I don't know, I don't remember. I think you have to put a prime number here, like 13 or something, and I don't remember what you do for Q. Yeah, I don't remember. I think you have to, I would have to look up numbers to get this to work, but I remember I did get it to work though, which is actually pretty cool. Matrix. I totally forgot what this was. This is just a program that it's supposed to look like the Matrix, just characters falling down the screen from the top. I can show you how I made this, or we can make it from scratch or something like that if you want. So there's just a whole bunch of different, things we can do. So this is just I guess I'm just showing, the other programs that I've made. This isn't, definitely not all the programs I've made before. I've made Tetris. I've been more successful with Tetris on the computer, on using QBasic. When I was younger, I made a really colorful, use up the whole screen Tetris game. But on the TI calculator, I've always had trouble getting it to run quickly. But I did get a decently fast enough Tetris game where you could actually, it was basically playable. It was fast enough where you could play it decently. But I don't, it's been deleted since then. So I remember I programmed it pretty quickly, but it was pretty long. It was a lot of work to try to replicate that. I don't know. I would probably just try from scratch. But it would be definitely a project. It would probably take a few episodes to get through that, and hopefully I wouldn't have something crazy to debug. So yeah, the fall down the fall down game is still, I still feel like I wish I would have conquered it better and understood what was going on. Usually when I design things, I like design it on, sometimes I design it on paper if it's complicated. That way I know exactly like what's going on, what variables are, how they're related to other variables. Like that's one of the hardest things for me to figure out when I'm just like programming by scratch, but I can't really picture all that at once. Is to figure out how variables actually, what they're doing, because I introduce a lot of them, but then they're interrelated in a very complex way sometimes. So here's our Zelda game that we've been working on. Obviously you know about this because we programmed it together. We got the pause screen. We can select different items in the inventory. Can't really select them yet, but we can move around the selector, which is awesome. Oh yeah, in the background reappears. So we have a nice like structure here. One of the things that I wanted to do, and I don't know if I should get started on it for this episode, or for if this episode I should just, you know, stick to, maybe I should just stick to showing you, you know, my programs, so I can just use this episode. I guess we could just say this episode, you know, is just a way to show all the programs and stuff that I've made. So it's a nice, what's random do? Oh, I think what that did, yes, okay. So one thing about, there's like this algorithm that basically, if you want to take a set of numbers, there's so many uses for this, but let's say you want the numbers 1 through 6, but you want them in a random order. But you only want each number to appear once. So you can start off with a list 1, 2, 3, 4, 5, 6, and then you can mix them. But an important thing that I've learned is the way I used to mix the numbers is I would randomly swap each number with another one. So I would take the first one, randomly switch it with, you know, one of these, including itself. So it could be anywhere. So bam, it could switch with, you know, one could switch with 5, and you know what I mean, they're in different positions. And then the second one, I'd switch it with any random one again. And then the third one, I would switch it with any random one, and so on and so forth. But actually, statistics, it's been proven, it's when you take that and you explore all the combinations and all the permutations, you actually have a favor towards a particular way of ordering things. You're favoring different sets of permutations than others, and it's not like an equal possibility, an equal chance for all possible permutations. The way to do that is when you swap them, the first one I did correctly, you swap it with any random one, including itself. But when you get to the second one, this is very important for the statistics. And I can show you on paper, actually. I can show a small example using like 3 numbers, for example. I can show you all the permutations possible from it in equal likelihood, and the fact that none of them are favored over any other ones. But when you get to the second one, you only swap it with that itself or anything to its right. But you never swap it with the first one. And then when you get to the third one, you swap it with itself or any of them to the right, equal chance. But you leave the first 2 alone, and so on and so forth, until you get to the last one. When you get to the last one, you don't swap it with anything. It's already had its full chance to be swapped by everything else as this reduced. But, you know, I mean, if you do it that way, you will have a perfectly equal chance of any permutation occurring. And that's what this program did. And actually, I was trying to. It was my mistake because I was trying to teach someone some programming, and I was challenging him to do different programs. And I decided I wanted to do that as a challenge. I wanted to make him tell him to program a random number generator, a random order generator in linear time, and it took him a long time to figure it out, and he needed help and from other people, I think, to finally get it. But the whole time I thought I knew it correctly, but actually I didn't. I actually did not. I didn't even have the correct implementation myself. So that's an important thing. When you teach someone, you got to know exactly, what you're doing and what the implications are for everything. You can't make even the smallest of assumptions because mistakes can happen. So I was sorting numbers in linear time the first time, but I actually had to change my code just a little bit to make it actually mathematically a truly equal chance. Assuming that the random number generator is also a correct, random number generator, which theoretically I don't believe you can prove that it is, but it's very good. So assuming that this is a perfect random number function, I have to build my code on that assumption, and I have to make my code correct. So now my code is correct because A changes. I guess is the variable that it selects from. No, A. Yes, random integer from A to X is going to be the new number that I swap with. So anyway, those are my programs. I can't think of any. You already know what Conway is because that was episode, I believe, 3. You know what fall down is because that was episode 4, 5, and 6. That was not fun. I believe this is just the quadratic formula, so you can look that up if you don't know what it is. What's speed? Oh, this is a game where you press Great, I just got a big penalty. You press the letters as fast as you can. So it says to press R, so I press R as quickly as I can. And once I get, I believe it's 25 letters, then I get a score. And it also keeps track of a high score by storing it in a variable. All these times where I say it stores it in like a special variable, that special variable is basically like you can name lists. You can't really name like single variables, and you can't really name, I don't think you can name your own matrices in a TI calculator, but you can name your own lists. So like here's speed, this is where the variable's stored. And see, 3038 is like the high score for that game, or I guess in that case it's the low score, because you want the lowest time. But the theta here, this one's actually used for the challenge program. So the challenge program sets these variables before it runs something like the Hanoi Tower game or something, and it sets the rules that it wants the game to follow before it quits the game and returns back to the challenge program. But it's also smart, so you can go into a sub game and then you could press the on button and you could just quit the entire thing entirely. But these will already be set to 0 when you do that because it's actually smart. It'll set these to 0 at the beginning, so it won't get confused. You can exit the game almost any time, maybe even when it's transitioning. That might be fine too, because when you start the game it just starts from scratch anyway. So but it won't. What the point is, if you exit, let's say I run challenge and then challenge calls Hanoi, like it runs this program, if I exit like right away, it might have some numbers like still set in it. So next time I try to run something like Hanoi, it won't really run correctly the first time. But once I actually run this game though, it will set. See, these are the parameters it'll set. It'll set them to 0. So even if one of these numbers was still stuck in that list, the next time I run the game, they'll all be 0 anyway. So it's just a nice way to make. It's just a nice like set of memory, I guess you can use for programs to communicate to each other when you're not totally sure how they're calling each other, or what the context is. It's a way to give context to the program. But anyway, I feel like maybe working on Zelda a little bit because I want to make progress on that, and I'm not like sick of it anymore because it's been a while since we've worked on it. So I kind of have a little bit of urge to work on it, just a tiny bit. And maybe for our next episode, for episode 8, we can work on Zelda a little bit more. Maybe we can make. We don't have to program too much. Maybe we can just make like a couple of like places to walk around, so that it's not just an empty game. Maybe we can put in some walls and make some levels or something, and maybe we can make some kind of. Actually, the next thing we have to make on here, I just realized, is when we wrap the screen, we have to have information stored in a larger matrix of some sort. And so we'll actually have to either that, or we'll have to have a program that when it's called, it sets the matrix to whatever the coordinates are. So because I want to be able to, when I move right, the coordinates of where our screen is should change. So we should be able to have. I might even add like a map of some sort, maybe. Although it might be difficult to describe the entire screen with just one character. But if that's possible, I might add that in later on. But yeah, being able to move like from this screen to like the next screen, and then the next screen's a completely different screen. I definitely want to do that. Because that'll be very important for actually making the game, similar to the real Zelda game. So that's it for episode 7. Thank you for watching, and I'll see you again next time.